All right, in this example, there is supposed to be a diagram that's drawn for you already, so I'm going to go ahead and you guys can write this piece in here. But it's basically you have two people that start off at 50 feet apart. Right, so there's a 50 feet. And then one person starts walking north, and so then we want to figure out this angle. As this angle changes at a constant rate at 0.01 radians per minute, how this distance between these two people, pretending that's a straight line, how this distance between these two people changes. So as this person walks north, this person can kind of like turn and watch them as they go away. And so then the angle between them would be changing, okay? And so that's basically our diagram that we're going to start off with, and we're going to go from there. So let's talk about the things. That would be step one. For step two, we talk about the things that we know and don't know. So right off the bat, we know that the 50 is there. We know that the angle is changing at a rate of 0.01 radians per minute. So we know that theta time is 0.01 radians per minute. We want to know the rate at which the distance between them is changing, so that's our unknown variable. And they want to know at what rate is that changing when your theta equals 0.5 radians, okay? So now, looking at this diagram, we want to be able to write a relationship, an equation that relates the theta, the z, and then probably the 50 as well. So in a right triangle, if you have an angle and then you know some of its sides, from this angle, this would be your adjacent side and this would be your hypotenuse side. So thinking about that, the equation that you could write to relate those three pieces would be using your trig function, excuse me. So you have cosine of theta would equal your adjacent side over your hypotenuse, right? Cosine, SOHCAHTOA, cosine is adjacent over hypotenuse. So cosine of theta equals 50 over z. And so then now we can implicitly differentiate that. This is step 4. Derivative of cosine of theta is negative sine of theta, and what we say implicitly differentiate because technically we're taking the derivative of each of these variables with respect to time, so you have to tack on that notation, right? The derivative of theta with respect to time. So negative sine of theta, d theta dt, and then we'll get on this side, another way to write this is secretly 50z to the negative 1. So if I took the derivative of that, I would get negative 50 over z to the 2, and then tacking on that dz dt. Awesome. All right, so then we know d theta dt, and then we have dz dt. Oh, no, sorry. Well, that's what we're looking for is dz dt, and we know theta. So it looks like the only other variable that we need to find first before we can actually plug stuff into this derivative is your regular z. And so in our previous example, when we used Pythagorean theorem, we used the derivative of it, but then you also had to use just the original function to figure out what your y variable was. And so before we even plug anything into this derivative, I'm going to use this original function to figure out what our original z value was. So if I know that cosine of theta equals 50 over z, cosine of my theta at that time, which was 0.5 radians, would have to equal 50 over z, and then you can solve for z from there. If you multiply it by z on both sides, and then divide by that cosine, you'll be good to go. One of the things that you want to make sure is that your graphing calculator is in radians because calculus, all of AP Calculus is measured in radians. All right, so for my z variable, I got 56.975. Rounding to 3 decimal places, and so then now I technically have that z, and so I can now plug everything into my implicitly differentiated equation. So I have negative sine of 0.5 times 0.01, because that's my d theta dt, and then I have negative 50 over 56.975 times dz dt. So basically, I'm just going to do all of this part in my calculator and then divide it by whatever that number is. So negative sine of 0.5, close those parentheses, times 0.01, and then that press enter, that divided by, parentheses, -50 divided by 56.975, end parentheses. So I get that my dz dt is approximately 0.005, and then let's make sure we get our units straight on this one. Z distance would be measured in feet, and then our time is being measured in minutes because it was radians per minute. So that is the rate at which your distance between the two people is changing. And I believe that step 5 here was plugging in your actual, substituting in your actual values you knew, and then step 6 was making sure your derivative or your final answer had units on it and that you could explain what it means. Awesome. All right, let's go on to our, it looks like our last example, but it's got 2 parts. So we have an example for a tank of water in the shape of a cone is leaking water at a constant rate of 23 feet cubed per hour. The base radius of the tank is 5 feet, and the height of the tank is 14 feet. So I'm guessing if it's leaking and it's a cone, I guess it technically doesn't matter, but I will draw my cone upside down. And there's a couple of things going on here. So there is the tank information. So I know that this tank has a radius of 5 feet, and then it has a height of 14 feet total. But then it also is talking about water inside of your tank. So, whoops, if this was like filled up with water, that means you're just not happy with my drawings up there right now. That means your water is going to also have a radius that's changing, but we don't know necessarily what's happening there. And then also that the height of the water would be changing as well, because water would be leaking out of the bottom. So that's important information to write down right off the bat about your cone. So step 1 is to draw your cone and the important information. Step 2, let's write down all of the things that we know. So we know that the water is leaking out of the tank at a constant rate of 23 feet cubed per hour. Remember, if you have a cubic quantity, that means volume. So I would say that the volume of the water is changing at 23 feet cubed per hour. And since it's leaking, it would be negative. So negative 23 feet cubed per hour. We also know in part A, it says at what rate is the depth of the water changing, or I called it height, I guess, is the depth of the water changing. So we're looking for dH dt. That's our unknown, when the depth of the water is 6 feet. So when the height of the water is at 6 feet. Awesome. And so then now we're going to kind of go from here and we're going to write an equation that relates volume and height of a cone. And this could be another one that your APTS actually gives to you, because I don't know if they expect you to know the volume of a cone, but the volume of a cone is 1/3 pi r squared h. And so then we're going to go ahead and we want to implicitly differentiate. Now, before we do that, though, I do want to, this is a very typical thing that pops up in cone problems. We run into a bit of an issue because right now I have volume and I have height, which is the two things, or which are the two things that I wanted to relate, but I also have this r in there, this radius, and I literally know 0 pieces of information about r. I don't know at what radius it's happening at. I don't know the rate at which your radius is changing. And so this is where it becomes a little more obvious, well, not, it will be once you've practiced these problems enough, that they needed to give you information about the tank, because you're going to use the information about the tank to rewrite this so that it doesn't have any r's in it anymore. And I'll show you what I mean. So one other piece of information that we know about this tank and this water is that they're proportional. So the tank is never going to change. So the tank is still going to have a 5-foot radius, or the base or the top of the tank is 5 feet and as the radius, and then the height is going to be 14. Well, that's always going to be proportional to the water. The water's not all of a sudden going to just like start sinking on this side and then stay high on this side, right? And so one other thing that we can write for this cone problem is that the radius over the height of the water is always going to be proportional to the radius and the height of the tank. Now this is good for us because now what we can do is I can rewrite this. I can solve this for r, so I'll multiply by h on both sides. So r will equal 5/14 h. And now what I can do is I know that no matter what my radius is, I can rewrite it like this. So in this equation, instead of writing an r, what I can do is I can rewrite it as 1/3 pi 5h over 14, whoops, squared h. And then we can rewrite it one more time to simplify it more. So you'll end up, let's see, with a 25 pi h cubed. And then on the bottom here, we'll have, let's see, 3. And then when you square 14, oh goodness, 14 squared times 3 would be a 588 on the bottom. And so now this is an equation that relates just the two variables that we actually have information about. So that's what's a little bit tricky about your cone problems. The same thing could happen with like a cylindrical problem or a cylinder. All right, so now step 4, we're going to take the derivative of this, implicitly differentiate it. So we'll have, it looks like dv dt equals, and then the derivative of this would be bring the 3 down, and let's simplify that fraction right off the bat. So 3 times 25 divided by 588. Math, enter, enter. So really this becomes 25 over 196. Pi is still there, and now it's an h squared, because I just brought that 3 down and multiplied it by this number. And then dh dt. Lovely. Okay, so then now we know, let's see, we know dh dt, we know h. Oh no, we don't know dh dt, that's our unknown. I was like, why do we know everything? And then h, and then we know dv dt, so now we can plug everything in for step 5. So dv dt is negative 23, 25 over 196 pi. And we know h was 6. And then we can solve for dh dt. So I would just do negative 23 divided, like you can calculate what all this stuff is together, and then do negative 23 divided by that number, and that's how you end up with your dh dt. So let's do that. Negative 23 divided by parentheses 25 over 196 times pi times 36. And I get negative 1.594. And let's see, that would be, volume was feet cubed, so this would just be feet per hour. And that makes sense because if our volume of the tank or volume of the water was decreasing, your height of the water should also be decreasing. It's leaking out of the tank. So that can kind of help you make sense of your answer, or at least make sure that it follows the same kind of structure as your beginning. In part B, we have at what rate is the radius of the top of the water in the tank changing when the depth of the water is 6 feet. So now it's the same picture as before. So step 1, we've already drawn a picture. And you can still see it on your paper. Step 2, we want to know at what rate is the radius of the top of the water changing. So we want to know dr dt. That's our unknown variable. When the depth of the water is 6 feet, well, that's h equals 6, and then we actually already know another piece about h, right? We know dh dt because we just found it in our last part of this problem. dh dt was negative 1.594 feet per hour. And so then now we want to write an equation that relates radius and height, and luckily we already did that up here. So instead of relating volume and height, we're relating radius and height, and then I'm actually going to use the simplified version of this just because I don't want to deal with quotient rule if I try to derive r over h. So this is my equation, r equals a 5/14 h, and then I implicitly differentiate, which gives me dr dt equals 5/14 dh dt. And I know dh dt, and I'm solving for dr dt, so this works out really well. Negative 0.569. Awesome.